All right, continuing in this section, we're going to look at piecewise functions. That's a mouthful. Piecewise functions. Functions just meaning that the graph that we're going to produce here is going to pass the vertical line test. And piecewise just means that it may take more than one equation to produce this graph. So studying what we have here, this is actually a piecewise function. And so it's kind of good to look at the structure of what a piecewise function is. It's not just one equation, it's more than one equation. So for example, we have the equation f of x or y equals this equation, x plus 3. This is a linear equation. This is when graph is going to produce a straight line. And that's because it's a polynomial where the highest degree is 1. So y equals the equation x plus 3 as long as the x values on this graph are less than or to the left of -2. Okay, we call what's in this kind of column right here restrictions on x. Restrictions. So if we think about this for just a second, where x is equal to -2 on the x-axis, which is just about right here, I'm going to kind of draw in this dashed line just to represent that we have a break in our piecewise function. Meaning that for x less than -2, or to the left of x values equal to -2, over here, we're going to want to graph what this looks like, this linear function. But after x is equal to -2, and when x is greater than or equal to -2, now we drop down here and we say, to the right of this kind of vertical place right here, over here on this side of the graph, now we switch and we're going to draw a different line. We're going to draw the linear function x minus 3 on the restricted x values where x is greater than or equal to, remember this means or equal to, -2. So we're going to have like two lines that are on here, two pieces of lines on here. So piecewise, meaning you have multiple equations in a function, this graph will still pass the vertical line test. So our objective in this video is to learn how to graph piecewise functions. So before we do that, I'm going to come over here and there's another worksheet where I'm going to kind of support us in learning about piecewise functions and then also review a little bit of past content. I like to kind of cycle old content through as well. All right, so you should have this worksheet right here, and actually it's the same worksheet if you've got it printed out. It's just the same functions up here and then the answers are down here. So I'm actually just going to kind of fold this right here. So let's not look at the answers right now. Let's just kind of look at what we have here. So let's talk a little bit about piecewise graphs, piecewise functions. So this is a function because this graph will pass the vertical line test. Notice that there's a lot going on here. It's very busy. There's a lot of pieces that make up this function. We have this piece, I'm going to work from left to right. We've got this first piece here, which appears that all the y values are up here at 2, up until you get to, when I read down here from the x-axis, x is -3. So the first piece, there's multiple pieces. The first piece is just y values of +2 on x values that are less than to the left of -3. When we reach this point right here, we have to lift our pencil, causing us to have a discontinuous graph. We have to jump down here vertically, and this is supposed to be a filled-in circle. And then starting at x values of -3, we have a linear piece up until we get to x values of -1. So, and then after that, we have this portion of this graph right here that's a parabola. It's a quadratic equation that graphs as a parabola. Okay, so we stay on this graph until we reach this high y value of 4. And then we no longer want to be a quadratic or a parabola. We jump down. And notice this circle right here is not filled in. It has to be open because we can't have, to be a function, we can't have two filled in circles. So we've got this linear piece here that's flat, horizontal. Then we have this linear piece that has a positive slope, or increasing. Then we have this parabola. And then we jump down here to this open circle and we have another piece that's linear. It's a straight line with a negative slope. Once we achieve getting down here to this point, then we jump back up with another open circle, and then we continue on this line right here. So if you kind of count all the pieces that make up this discontinuous piecewise graph, we've got 1, 2, This is an equation right here, 3, we have 4, and we have 5. So actually for this piecewise function, there are 5 equations. So I'm going to kind of display this. And when I created this graph, I used a software program, and I input this piecewise function. So let's see if we can kind of make some sense of these equations and these restrictions on x as they apply to this graph. It will only help us when we go to graph a piecewise function. So it says for our, well, first of all, we count 1, 2, 3, 4, 5. We have 5 pieces, which we saw right here, evident in the graph. And we only want these equations or these graphs, these 5 different graphs, based on these restricted x values. So let's see if we can kind of correlate these equations with the different pieces here. So y equals 2 as long as the x values are less than -3. So I would come over here and find where x is -3 right here. I'd cover everything else up. If x values are less than -3, I want to consider what's to the left of x equals -3. And it says all the y values have to be at a height of 2. Well, we saw that earlier that they were. So we're graphing a constant here, a flat line. Now let's fall down here and look at the restriction on the next x's. So what happens in this case right here? Well, it says x is between -3 and -1. So if I kind of only display that, here's x equals -3 and x equals -1. So let me cover up everything else. It says that how I got that part of the graph, the piecewise discontinuous graph, is that I graphed 1x plus 2, or just x plus 2. I just kind of showed that little 1 there. So that actually is going to graph this little piece right here. It's a linear function, a line, okay, between the x values of -3 and -1. Something to point out is it's or equal to on both sides of these numbers here. So if you want to include these x values, we indicate it with a closed circle. All right, let's jump down to the next piece. Let's look at y equals x squared. Well, we saw that earlier, that y equals x squared is that parabola that has this kind of basic shape. But notice that I don't have the whole entire graph here, because if I did include the whole entire graph, I wouldn't have a function. I only want y equals x squared on x values between -1 and 2. So here's x equals -1, and here's x equals 2. So cover everything else up except for that interval of x's. Well, that looks like the part of the parabola that I graphed in our earlier lesson. So that's good there. Let's look at the endpoints, meaning notice that x is greater than or equal to -1. We kind of read from the middle to the left and then from the middle to the right. So if x is greater than or equal to -1, I need a closed circle here. Well, there was already a closed circle because of the previous piece, and they actually meet up in the same location. Okay, why do they meet up in the same location, the same y value? Because if you plug -1 in for x here and add 2, you get -1. If you plug this -1 in here for x and square it, you're going to also get 1. So these two graphs right here meet at the same y value. Okay, but on the other end, look at where it says x is less than or equal to 2. So come over here to where x is 2, look up. So because we have or equal to, we do want to include that point with a filled in circle. Had there not been an or equal to, that would have been replaced with an open circle. Well, let's look at the fourth piece. So on the restricted x values between 2 and 3, including 3, so here's x equals 2 and here's x equals 3. I want an open circle on the left at x equals 2 and a closed circle on the right at x equals 3. So right here, I'm graphing another linear function with a negative coefficient on x, which means my linear function is going down. It's decreasing. And the final piece that I'm graphing for x values greater than 3, so if x is greater than 3, I'm looking at just this portion of the graph. I've got another linear function, another line, but I only want part of it because I only want where the x values are greater than 3. So how do you know where it starts? Well, we could plug 3 in for that x, subtract 2, and we're going to get 1. So we end up plotting 3, 1. So this is 3, 1. And I'm going to put an open circle there because I don't have an or equal. I know that was a lot, but I thought, well, if we kind of spend some time front loading this, and you can kind of look to see that this is a discontinuous piecewise graph made up of 5 different parts. and where those came from and the structure of the equations and the restricted x values for each of those pieces, it's going to help us when we go to have to plot some piecewise functions. All right, so let's leave that for just a minute. We'll return, but in the meantime, let's just kind of review some content that we've already covered in this piecewise graph. So if you want to pause the video and see how many of these questions you can answer based on what we've learned so far, and then you come back and check your work. All right, we're asked to find the domain, and we're going to use interval notation. Well, you could either look at, my equations that I had to see what all of these x values encompass, put all these x values together and come up with a domain, or you can just visualize the domain from the graph. I know that the graph continues to the far left, so if I come from the far left, I'm still on the graph, The only time I might not be on the graph is right here. However, because I have this filled in circle, this x is part of my domain. So I'm going to continue with my pencil, moving it across. I intersect the graph right here. I'm going to intersect that closed circle. So at x equals 2, that's part of my domain. It's okay that this is an open circle at x equals 2 because x equals 2 is included. So then I continue. When I get to x equals 3 is part of my domain, so it's okay if I jump up. I have an open circle, so any of these x values which are greater than 3 are part of my domain. So really our domain is that we can have any x value on the x-axis that would be an x-coordinate of a point on this graph. All right, let's look at range. Okay, I'm kind of observing the behavior of the graph here. I see that I have the graph ends in a closed circle here. I don't see any arrows suggesting that I go downward. So when's the first time using my pencil that I'm going to intersect a y value? Well, that's going to be right here at that point. If you come over here and read the y value from the y-axis, okay, the first time I'm going to have a y-coordinate of a point on my graph is at y equals -1. So I'm just going to slowly move my pencil up, and as long as I'm intersecting one or more pieces, doesn't matter how many, one or more pieces of the graph, okay, that's going to be part of my domain. Now right here, I'm observing that this part of the graph is going to end here. However, we do have this arrow that suggests we go upward to infinity. So I know that as I continue upward, I'm going to have y values go into infinity that are part of my range. So my y values start at -1 and they go to infinity. So the only other question is, do I include, we always put a parenthesis around an infinity, never a bracket. Do I need a parenthesis or a bracket around the -1? Well, because it's a closed circle, it's inclusion, we use the bracket. All right, x-intercepts. Does this graph have any x-intercepts? Well, I always kind of sweep my eyes from left to right on the x-axis because that would be where you have x-intercepts, where the graph touches or crosses the x-axis. So right here I have an x-intercept. We always reported x-intercepts as ordered pairs. So if you need to put a little note over here to yourself and say ordered pairs just to remind yourself, that might be a good idea. Another time where my graph touches or crosses the x-axis is at x equals 0. When y is 0. Continue moving to the right. Oh, there's another x-intercept. I can either touch or cross. This one's touching. So that x-intercept is 3, 0. Notice all the y's are 0, and that's the case with the x-intercepts. All right, y-intercepts. I start from the low y's and move to the high y's. Do I have any crossings or touchings with the y-axis? Well, I do right there. The origin is going to be both an x and a y-intercept, and we write them in ordered pairs as points. Remember, in this context, the parentheses don't mean everything in between. It just means a location on your graph. Okay, I'm going to skip this for now, and I'm going to come over here. Increasing intervals. Remember, we report increasing and decreasing intervals, okay, using x-coordinates. And it's always parentheses, never brackets. So where is the graph increasing? Here, and here, and here. Right, so if the graph of the function is increasing in this location, we want the x-coordinates where that's occurring. So we can see from x equals -3, and then from to up till x equals -1, from x equals -3 to x equals -1, the graph of that function is increasing. The graph increases from this x coordinate of 0, if you bring this to the x-axis, to x equals 2. The graph is also increasing from from right here, x equals 3, and we're going to put a parenthesis on it anyway, and then it just continues increasing to infinity. All right, let's do decreasing intervals. Well, that would be here and here. So for decreasing from x equals -1 to x equals 0, and then from this x coordinate, read from the x-axis, is 2 to this x coordinate, which is 3. We do have a constant interval, and it's right here. And the arrow suggests that we come from -infinity and we stop being constant at x equals -3. Always parentheses, never bracket on this content question. Okay, let's come down here. Okay, what does this mean for us to find? It's been a while because we've had a couple of lessons, but this is saying from a graph, let's find the y values when these are our x values right here. We're evaluating the function when x equals -4. So where x is -4 is right here. Look up because that's where the graph is. What's the y value here? Read it from the y-axis. So that means that the functional value is 2. Another way, as a reminder, to write that as an ordered pair is -4, 2. And certainly -4, 2 is a point on the graph right there. So it's f of 2. Well, here's x equals 2. Look up. Can't choose this as my answer because it's an open circle. I got to continue until I have a point, and that's at a y value of 4. So what that means is that the point 2, 4 is on this graph, which makes sense, 2, 4. And f of 3, well, that y coordinate is just 0. Another way to write that is the point 3, 0. Okay, this is kind of an extension question here. This says, find the x's for f of x equals 1. So notice that I have to find the x coordinates where the y coordinates are 1. Remember, this is a y. So I go up to where y is 1, and I look to my left, and I look to my right. Okay, so I know that a height of y equals 1 occurs here. What's the x coordinate? We'll read it from the x-axis. That's -1. Is there another intersection of my horizontal line at y equals 1 with the graph? Yes, right here. This point has a height of 1. Well, what's its x coordinate? Well, it's +1. Continue to the right. The next time I intersect the graph is right here. Well, that x coordinate is actually halfway between x equals 2 and x equals 3, so we'll say 2.5. And if I continue, notice that this height of y equals 1, we see that we have an open circle here, so I can't include x equals 3 because that's an open circle. It's not included. If that had been a closed circle intersecting with this horizontal line I have here, then I would put 3, but I don't have that closed circle there. So I know that was a lot, but we did look at piecewise functions and we did kind of spiral in some review. So now it's time to go back to our objective, which is to graph a piecewise function. All right, so how do we tackle graphing piecewise functions? Well, I would suggest creating a t-chart for each of the pieces that are present. So right here, we've got two pieces, f of x equals x plus 3 and f of x equals x minus 3. So when I'm asked to graph a piecewise function, I go, oh, okay, I got two pieces. So I'm going to use this space right here. So I'm going to create two different t-charts. Okay, down the left column, I'm going to put my independent values, x here, it's independent. My inputs are my domains. Now, unlike in the last video where I always use -2, -1, 0, 1, and 2, I can't do that for this piecewise function because of these restrictions. I have restrictions now that don't allow me to kind of pick and choose. I mean, I can to some degree, but I have to kind of follow along with the restrictions. So let's look at this first column, this first T chart. So I'm going to put my x here. Now my y is going to be this top piece. So you can either put y, but to be more descriptive, let's put x plus 3. We also need a t-chart for this equation. So my input is x and my output is y equals, but I want to be more descriptive and put x minus 3. All right, let's start building the values that belong underneath the x column here. So what x's can I put down here because I'm on x plus 3? Well, I've got to slide my eyes over here and go, oh, I can only choose x values that are less than -2. Well, -3 is less than -2, -4 is, and -5 is. I would recommend, even though you don't have an or equal to here, I would go ahead and put -2, the x coordinate of the break. I'd go ahead and put it here. But out to the side, I might put a little open circle because I know if I don't include x equals -2 and it's less than, I want to get as close to x equals -2 on my graph as I can. So I'll put an open circle here. Let's go ahead and build the x's that belong here, and then we'll finish the tables and plot the graph. All right, remember we're on x minus 3. That's this bottom piece, so we slide our eyes over here. I can only put x's down this column that are greater than or equal to -2. So I'm going to put -2 here. So I usually start the two different columns with the break of the x value. But I'm going to put a filled in circle here to remind myself that when I plot this point, it's going to be a filled in circle because of the or equal to. So then, okay, then I think about what are some x's that are bigger than -2? Well, you're moving towards 0, and then you're in the positive numbers. I think 4 numbers are probably good enough. If you feel like you need more than 4 x values, then you can certainly, follow the pattern, that needs to, for the x value that needs to belong there. I think this would be good. Okay, so now what do we do? Well, in this t-chart, we're going to take all these x's and replace it in for this x and find the output and put it along the corresponding input. So when x is -2 and we add 3, we get 1. When x is -3 and we add 3, we get 0. Plug in -4, we get -1, and likewise, we're going to get -2. Let's go ahead and generate the values, populate this column. But now we have to plug these x values into this equation because these are the restricted x values for that equation. When x is -2, I subtract 3 and I get -5. -1 goes in for x, minus 3 is -4. 0 minus 3 is -3, and 1 minus 3 is -2. Now what we do is we go and we take all these ordered pairs and we place them on this graph. Okay, so let's think about this t-chart. We've got -2, 1, -2, up to 1. But remember, we are on this piece and we can't include that, so we do an open circle, and hopefully you have that there to remind you. Okay, where's -3, 0? Well, -3, 0 is here. -4 over here, -1. -5, -2. Are there enough points that suggest the behavior of this graph? Yep, it's linear. I would connect the points. I would draw off the grid with an arrow. So just kind of pull back and check and make sure, are these points in the places that they need to be based on the fact that this part of the graph should be on x values that are to the left of -2? Yep. So there's some kind of built-in, checks that we can do. So when I plot these points, they should fall over here to the right of or on x equals -2. So let's plot and see. So -2, -5 down here. Close circle, because the or equal on x minus 3. -1, -4, yep. 0, -3, and 1, -2. Do I have enough points to suggest how I connect them? Yep, like this. So if I were to continue putting x values down this column, generating the y's, the pattern suggests, the way I plotted them, that my graph is probably going to go off the grid this way. So I've got 2 linear pieces that make up this discontinuous piecewise function by creating t-charts and then plotting points. Okay, we'll have another example in just a second, but before we leave this, we do have these additional questions right here. Okay, based on the review we just did, what is f of -3? Well, we know that the x coordinate is -3, and if x is -3, we're right here. So the answer, or the y value, is 0. if we didn't want to evaluate from the graph, we could actually plug in, these are x's right here, we could plug in x equals -3 to the appropriate piece. I can't plug in x equals -3 to both pieces. -3 falls to the left of -2, so that means that I would plug -3 into this top equation because that's where the restrictions are, where x is less than -2 and -3 is less than that. So without looking at the graph, maybe we should try and use these equations to determine where I plug these x values into. If x is 0, how does 0 compare to -2? Well, it's greater than -2. So I want to choose the restriction that has the greater than symbol, which is right here. So I would plug 0 into this equation, subtract 3, and I'm going to get -3. And we're confirming that over here because that's where we found this ordered pair. F of -2. Well, where does -2 belong? Not up here in the top piece because we don't have the or equal, but -2 belongs to the bottom piece. So plug -2 in for x, subtract 3, just like we did here. So this functional value, or y value, is -5. So when given equations and graphs, you have a way to kind of check your work. You can either find the functional value from the graph by locating the x coordinate first and then finding the y, or if you know to look at the restrictions that will determine where you plug these x values into, the top or bottom piece, you could find the answer that way without relying on the graph. All right, let's go ahead and do some more practice problems. So I know we don't have any more room on this, but I've got the back of this sheet that I had done another practice problem for earlier, so I'm just going to use this space right here. All right, we've got two pieces that make up our piecewise function. We want y equals x as long as the x values on the graph are to the left of 0, not including 0. And we want y equals -x as long as x is 0 or greater. So the first thing I do is kind of draw a little grid, and I realize, oh, the restrictions have a break at x equals 0. So I kind of know that I'm going to have one equation that graphs over here to the left of x equals 0, and one equation that graphs to the right of 0 and on x equals 0. So I kind of get that going right there. And then I create those two T-charts. I've got two of them because I have two pieces. 1, 2 pieces, 2 T-charts. 3 pieces if I had them, 3 T-charts. So this would be y equals x, this is x, and this is y equals the second piece. Then I look up here at my restrictions. So x has got to be less than 0. Well, I'm going to go ahead and start with 0, but remember we're going to put an open circle here. So let's generate a few integers that are less than 0, like -1, -2, and -3. And when we plot these ordered pairs, once we get them, if that's not enough information to kind of, when we put them on here, to determine what the graph looks like, we can always add more. All right, so for the second piece, where y equals -x, I want values that are 0 or greater. So I'm going to just kind of populate that column with those integers. Now I'm going to go back and complete the tables. So when I plug in 0 for x, I get 0. Plug in -1, I get -1. Plug in -2, I get -2, etc. Now let's go ahead and populate this column. Plug in 0, opposite of 0 is still 0. Plug in 1, the opposite of 1 is -1. Plug in 2, the opposite of 2 is -2. So, and then we just kind of populate with -3. Now let's come over here and put these pieces on the grid. So I've got the ordered pair 0, 0, but it's an open circle. Then I want to plot -1, -1, so left 1, down 1, filled in circle. -2, -2, filled in circle. -3, I got it, -3. I have enough points here to tell me that I'm going to continue plotting points this way. So let me connect these points, draw a little bit further, and put an arrow. This table's complete. Now let's plot these ordered pairs. Oh, I meant to put a closed circle here. So sorry, because it's or equal to. So now I'm going to come and plot the point 0, 0, but it's going to be closed. Well, 0, 0 is already here with an open circle. So what happens is I actually fill that circle in. 1, negative 1, so here's 1, negative 1. Positive 2 is over here, and then negative 2 would be down here. Positive 3, which would be about right here. Negative 3, which would be about right here. I have enough points to understand that that's a linear function. I'd connect them, draw a little bit further with an arrow. So our piecewise function is actually continuous. I can draw this graph without ever lifting my pencil, just because of the nature of the graph. Okay, and one more. It's a little bit interesting problem. Okay, we've got y equals 4 if x values are less than or equal to negative 1, and we've got y equals negative 4 as long as the x values are greater than negative 1. So first thing, come over here, draw your grid. Where's the break occurring? Well, the break occurs at the x value of negative 1. I just kind of lightly dash in, or lightly draw in this dashed line, just to tell myself I've got to draw part of the graph over here to the left of x equals negative 1, and part of the graph, the other piece, is going to determine what's over here. Okay, how many t-charts? 2, this is x, this is y equals the top piece, this is x again, and then y equals the bottom piece. The x value of the break occurs at negative 1, so I'd put negative 1 as my first x coordinate in both t-charts. Okay, for the top piece, I can include the negative 1, so I'm going to put a little closed circle here. But in the second piece of negative 4, I don't want to include the negative 1, so just a reminder that I have to put in an open circle there. All right, now, so what numbers go down here? We'll take a last look up here. X values less than negative 1 would be negative 2, negative 3, negative 4. Okay, what goes down here? We'll connect back to the piece that's y equals negative 4. X values greater than negative 1, which means you're getting closer to 0, and then some positive numbers. This is an interesting problem because of these equations. Notice that neither one of these pieces have an x in it. So do I have a place to plug negative 1 into? No, because I don't have an x. So my answer is actually just what y is. All these y's are going to be 4. Negative 2 has no place to go in for x. So my y, and that's what this is saying, all these y's are 4. Just like down here underneath this column, all these y's are going to be negative 4. So we're going to have some constant graphs. Let's plot negative 1, 4. So negative 1, 4 filled in circle. Negative 2, positive 4. Negative 3, 4. Notice how all these points are lining up horizontally. Well, I could plot the last one if I want to, but I still can see that I'm going to have this constant function this way. Double check, make sure everything looks good. Yes, this piece right here should have been graphed to the left of x equals negative 1. Now let's plot these points. Negative 1, negative 4. So negative 1, negative 4. Open circle, because we don't include the negative 1 here. 0, here's 0, x is 0, negative 4. And then 1, negative 4. Here's 1, here's negative 4. Then 2, negative 4. And it goes on and on and on. So I'm going to come back here and I'm going to start connecting all these ordered pairs. They're going to line up horizontally. I'm going to extend a little bit with an arrow. So hopefully that was enough graphing of piecewise functions to kind of get your mind around how you would approach it. So I would look at my piecewise functions. I would go ahead and set up my grid, represent a dashed line to represent where the break is, create as many t-charts as you have equations, and then really pay attention to what kind of x's you should put down these columns based on the inequality symbol and these restrictions right here.